We saw that straight line solutions such that y prime equals lambda times y for a constant lambda to linear systems of differential equations given by y prime equals a times y satisfy a times y equals lambda y. We also found that if the determinant of a is non-zero, then the only solution to the system of equations a times x equals 0 is the zero vector itself. We will use both of these ideas to get a better understanding of the straight line solution. We will start by giving a definition to constants lambda and vectors v that satisfy the above equation we found to be true for straight line solutions. A times v equals lambda v. We call lambda an eigenvalue with eigenvector v, which is not the zero vector, if a times v equals lambda times v. Notice that if we allowed the zero vector to be included, then lambda could be any value paired with the zero vector, since a times 0 would equal lambda times 0 no matter what matrix A we had and value lambda we had. Since the straight line solutions launched this definition for us, we can see that these eigenvalues and eigenvectors play an important role in the straight line solutions to our linear systems of differential equations. So we need to study how to find them. In our equation a times v equals lambda times v, we have different types of multiplication. On the left, we're multiplying a matrix onto v, and on the right, we are multiplying a scalar onto v. To have the same type of multiplication, recall that we can replace the scalar multiplication lambda times v with the matrix multiplication lambda I, where I is the identity matrix, times v. With this, we can rewrite our equation a times v equals lambda v as a times v equals lambda iv. And since we have the same multiplication now, we can subtract lambda iv from both sides and factor it out. So we're left with a minus lambda I times v equals 0. But we said above, if we have a matrix times a vector and get the zero vector, then either the determinant of that matrix is 0 or the vector is 0 itself. Since v is not 0 by definition of an eigenvector, we must have that the determinant of a minus lambda I is 0. So we can conclude that if lambda is an eigenvalue of a, then the determinant of a minus lambda I equals 0. And this will give us a way to find our eigenvalues. For a 2 by 2 matrix A, which we can write as A, B, C, D, this can be interpreted as the determinant of a minus lambda I, which is a minus lambda, b, c, d minus lambda, must have determinant 0. But we know how to compute the determinant of a 2 by 2 matrix. We'll multiply the entries on the diagonal, a minus lambda times d minus lambda, and subtract the product of the entries on the off diagonal, b times c. So we have a minus lambda times d minus lambda minus b times c equals 0. And distributing the left-hand side, we'll get lambda squared minus a plus d times lambda plus ad minus bc is equal to 0. This gives us a quadratic equation that we can solve to find the eigenvalues lambda. And this equation itself is given a name. We call lambda squared minus a plus d lambda plus ad minus bc equal to 0 the characteristic equation of A. Before we compute the eigenvalues for an example, I want to point out a couple of notes about this characteristic equation. Notice that the constant term ad minus bc is the determinant of A, and lambda's coefficient is the negative of the sum of the diagonal, a plus d. This sum of the diagonal, a plus d, is called the trace of A, and written as tr of A. Those of you that have taken linear algebra before may have seen this. If not, it's not an important issue, but something to note. So using this language, we have that the characteristic equation of A is lambda squared minus the trace of A times lambda plus the determinant of A equals 0. And we can find these eigenvalues by solving this quadratic equation. And for each eigenvalue lambda we find as a solution to the characteristic equation, we can find the corresponding eigenvector v using the definition of an eigenvalue and eigenvector. In particular, that A times v is equal to lambda times v. In the next video, we will look at an example of this.